Okay, so in this talk, I will talk about optimization for machine learning and current challenges that machine learning is facing in terms of optimization, and which means how to really train the neural networks or similar optimization models. So to start, I will firstly introduce what supervised machine learning is. Okay, so let's suppose that we have some data points AI, some labels BI for I between 1 to n, and here n is the dataset size. So you can think of it number of the data points. The thing we really care about is something like that, average over some loss on prediction AIX BI, where x is the model parameters. So what this really tells us that these AI BIs are data and labels. So this prediction AIX is essentially trying to really guess the label BI. And if we guess the label BI correctly, this loss is small. So ideally, we want this average over endpoints of this thing to be small. So therefore, what we really try to do is find model X such that average over n functions is small, and those n functions can be written as this loss prediction AIX BI. Okay, so this is what we are trying to solve. Okay, so to give you a better idea about what this really can be in different applications is the following. So this AI BI, which are the data, can come from various sources. They can be some vision data, so where we are trying to distinguish whether some image is cat or dog. Those can be language data, where we try to understand some language or do translation from one language to another. Those can be medical data, whether it's about detecting cancer or something like that. Next, this prediction of AIX can be really anything. For example, it can be some neural network. So given AI, which is image, this prediction AIX can be different layers of some convolutional neural network or recurrent or attention, or there can be all kinds of different layers. But what this X really is, those are weights of those specific layers in this case. On the other hand, this prediction AIX can be also something else. This can be some simple linear model, or it can be some decision tree, or really anything you can think of. And this loss also, essentially, it can be anything, but usually for classification, people use softmax cross entropy, and for regression, people use squared loss. Okay. So let's firstly give us a quick idea about classification, which is one of those two applications I mentioned in the last slide. And so the point of classification is that we have some points in the space, let's say red points and green points, and given coordinates of specific point, we would like to really be able to say whether it's green or red. So let's say that the first point is, in this case, AI, second point is A2, third point is A3, and so on, end point is AN. What we want to find here is model X, and model X in this case is some kind of line which separates those two things. So that if a new point comes and it's above that line, we will guess that it will be red, and if it's below that, we will guess that it's green. Okay, in this specific case, we can say that this prediction of AIX, which was mentioned already a few times, will be just simple dot product of AI and X. And this BI, which are labels, let's say it's just 1 if the point is red and -1 if the point is green. And this loss function, which we mentioned already a few times as well, we designed it in such a way that it's small if BI times prediction is large. So if prediction gives some really large number, that means that the model is that means that the point is either far away to one side or far away to another side from the line, so that it's kind of certain. So ideally, we want, this loss to be small if BI times prediction is large. But this loss can be essentially anything. People use often softmax cross entropy, but it doesn't really matter. I will not really talk about what it is. Another application that I mentioned is regression. And in this regression, what we have several points AI, which AI is currently just one-dimensional thing on this x-axis, and BI is the label, which is also some real number on y-axis. So for given AI, we would like to predict BI. Okay, so in this case, model X will be just this line or something like that. Ideally, we want to do something like that. And then given AI, we would predict something which is on that line. And ideally, we want then to difference between this prediction and the point to be as small as possible. So in this stupid and simple case, this prediction AIX will be again just linear function dot product between AI and X. And again, loss, we will design it in such a way that loss is small if BI is close to prediction AIX. Okay. And one specific way how to design this loss would be to just do squared loss. So this loss will be just square distance between the real label and our prediction. And we want to minimize that across the whole data set. Okay, so given we quickly introduced about what is the problem, let's try to talk about some very simple ways how to potentially solve it. So let's say that we want to do this, minimize f of x, and xk is our current guess on the optimum, or what the optimum would be, or the current model we think which is reasonable. So the question is, how do we improve it? How do we improve this xk? So it turns out that there exists such thing which is called gradient, which is really direction of the steepest ascent descent of the function value. So you can think of it that you are somewhere on some mountain and you are blindfolded and you can only feel by your feet and you want to go down. So you feel like, okay, this is the direction which is the steepest to go down. So if you want to go down as fast as possible, probably you will go that direction. So this is really what gradient is somehow telling us. And again, it makes sense then to move in direction of this steepest direction. And the new model or new guess on the model xk plus 1 will be just xk minus alpha, which is step size or learning rate. It's something rather small times the gradient. So we will do some small steps towards the steepest direction. Okay. Given we have that, let's see what it really does. So given that this is the function, where this green point is the optimum, and this red point is where we start, our current guess of the optimum, and those lines are just the contours. So those are the lines where the function is constant. So firstly, I mean, the gradient will point somewhere here. This direction will move, take a relatively small step, and move to the next point. Then again, we move in direction of the gradient and get the next point. Again, move in direction of the gradient and get the next point, and so on. So overall, we will, after some steps, get to the optimum. So the question is now, how fast or how efficient is that? And if function or gradient of f is Lipschitz, I will not really talk about what is it, but those who have some mathematical background, it really means that the gradients don't change too much or something like that. So if the gradient is Lipschitz, then the convergence rate of this gradient descent is something like that. So what is it really saying? So if function f is convex, this rate is O1 over k. So you can think of it that if you do 1,000 of iterations, your distance to the optimum decreases 1,000 times. If you do 1,000,000 iterations, the distance decreases 1,000,000 times. And yeah, but what is nice that you get to the optimum. On the other hand, if function f is strongly convex, which is something slightly stronger to assume, then this rate is something 1 minus something to the power of k. So this really means exponential convergence. So you can think of it, if the c is 1/2, then if you do k, which is 10 iterations, you get closer to the optimum 1,000 times. If you do 100 iterations, you get closer to the optimum 1,000,000 times. So this rate is somehow way stronger than the previous one. On the other hand, in many applications, the objective is non-convex, for example, neural network. However, it is nice that we still get 1/k convergence rate. That means that in 1,000 iterations, we get 1,000 times closer than where we were at the beginning. On the other hand, what is not that nice is that we don't get to the exact optimum, but we get to the stationary point. So stationary point is where norm of the gradient is small, or this really tells us that somehow around that area the objective is flat. There is no direction in which we can improve too much our objective. The ugly thing is that this doesn't need to be the global optimum. It can be the local optimum or stationary point. But in such case where the objective is non-convex, it's really hard to find the global optimum. And essentially, if one wants to find the global optimum, one needs to search the whole space. And especially if the space or dimensionality of the space is really large, this is really infeasible. So result of the type is somehow good, and this is roughly okay. So one, essentially, this gradient descent, one disadvantage of that is that it didn't see this finite sum structure average of many functions, which we assumed at the beginning. Remember that the problem we are trying to solve is we want to minimize average of n losses over n data points. And usually, what is the problem is this n, or number of data points, is big. That can be in practice millions or even more. So consequently, if you want to even compute this gradient of f of x, which is average of n functions, average of n gradients, average of gradient fix, what you really need to do is you need to go through the whole data set. You need to look at every single data point and compute gradient on every single loss. And this is essentially very expensive. I mean, if really your data set is millions of images, I mean, this will take a lot of time. So therefore, just to update your current model, even a little bit, takes a long time, and consequently, something like that is really infeasible way how to train those models. So the question is, can we do better? And it turns out yes, and the answer is stochastic gradient. So what we will do is that every time, if we want to update the model somehow, we will pick random index I, so random data point, essentially uniformly, and construct some kind of gradient estimator, which is just gradient fix. What is nice about this thing is that on average, I mean, if you take expectation over this choice of I, on average, I mean, this direction is good. However, it's good, and also what is nice about it, it's cheap, because to compute full gradient, you need n evaluations of those little gradients, and here we need only one. So it's n times cheaper and good on average. Question is it enough or not? Okay. And soon we will see that it does something. So if we have this algorithm, if we have this gradient estimator, which is gradient of fixk for random I, the algorithm which we will do is something like that. Just every iteration move in direction of this gk times some constant alpha k. However, in standard gradient descent, what was nice is that this thing always improved our model. Here, since this gk is somehow random, it may not always improve our model. And this is essentially reason why, I mean, what we really need for this method to somehow converge and do something good is this sequence of alpha k's to converge to 0. So we want those learning grades or step sizes decrease over time. And another reason why this is necessary is that if x star is the optimum, then gradient fi x star is not 0. So therefore, even if xk is the optimal or the best model we can ever reach, it turns out this gk will not be 0. So therefore, the how we update our model is we get something worse. So even if we are in the optimum, we must inevitably get out of there, which is problem, and this will somehow cause slow convergence. Okay, how does it really look in terms of, convergence rates? So again, if function f is just convex, then the rate of the stochastic gradient descent is 1 over square root of k. What it really means that if we do, let's say, million of iteration, we get 1,000 times closer to the optimum. On the other hand, gradient descent only required 1,000 iterations to get closer to the optimum. So therefore, gradient descent needs like 1,000 times, in this case, less iterations. But on the other hand, if this n number of data points is like million, one iteration of SGD is million times faster. So SGD will still be better. Next, if function is strongly convex, this rate of SGD is something like 1 over k, and if it's non-convex, is again 1 over square root of k. And again, we just converge to some stationary point with small gradient. So the takeaway from this is really only that stochastic gradient descent has cheaper iterations. On the other hand, it is slower, and to converge to the optimum, to converge to the exact optimum, you need way more of them. What is also less nice is that if you want this precision to be really small, gradient descent will usually converge there faster. And here is one stupid and small example where to show that. So here on x-axis is, on this graph, is number of calls or number of evaluations this gradient of this gradient fix, and on this y-axis is this relative error, or how far are we from the optimum. So we see that gradient descent is somehow steadily decreasing all the time with roughly the same speed. On the other hand, stochastic gradient descent at the beginning is really fast, but then slows down, and at the end doesn't get to the optimum as far as gradient descent. So if you want relatively low precision, stochastic gradient descent is good. If you want high precision, it's probably not good. So now the question is, can we do something slightly more sophisticated and still have some algorithm that has cheap iterations, however, doesn't have this issue as stochastic gradient descent, that essentially slows down and it's too much random? And the answer is yes. And that's this green line, and that's this Saga algorithm. And what is that thing doing is, like, every iteration, again, we compute some G, which is some gradient estimator. However, this one is somehow smarter. And the way how it's smarter is that its variance is smaller than variance of standard SGD. And the reason why it's smaller is that as xk converges to x star, like if we are closer to the x star, this estimator G is such that its variance goes to 0. Okay. And the question is now how to construct this G. How exactly do we do that? And the answer is we use control variants. Okay, so what are those control variants? So this is rather some standard trick in statistics, and people in statistics were using that for many years in the past. That was well known, but it is relatively new thing in optimization or new thing in machine learning. As you can see, two papers which really introduced those things were from 2013, 2014, so like 6 years ago. Okay, so what is that really doing? So as we said, we will construct some GK, which is some gradient estimator, and update model in the direction of some learning rate times GK. However, this GK will be something like that. It will be gradient fi xk, which is the same as gradient estimator in SGD. And what we will do, we will subtract some yk and add expectation of yk. So yk is something random. You can think of it as something random. If we choose, for example, this yk to be just 0 always, then this gk is just stochastic gradient. On the other hand, if we choose this yk to be gradient fixk, that what we will get is the full gradient. The reason for that is that, first of all, if this gk is unbiased, so if we take expectation over choice of y, then expectation of yk here kills itself with this expectation, and we get the full gradient. So I mean, on average, this direction is good. On the other hand, what we really want is this covariance of yk and gradient fixk to be high. So again, if yk is always gradient fixk, then those two things cancel, and expectation of gradient fixk is just the full gradient. Yeah. So therefore, we want this y to construct in such a way, again, that this covariance between y and gradient fixk is large. Okay. So the only question is like, how do we really construct it? So the simple answer is that, okay, it is somehow possible, and let's not care about it. But one simple intuition, I mean, how I will very quickly describe like how it's done. It's not that important. The point is just people construct it somehow on the fly. However, what do you really want? If you want yk to be somehow correlated with this gradient fixk, one should remember that if we are somehow close to the optimum, or if this alpha was 0, if we weren't really changing this xk at all. So in that case, and if we run sufficiently enough iterations, it turns out that we've already seen this gradient fix in the past if we run sufficiently many iterations. So we just set this y to be, last time we saw gradient fixk. And yeah, if this step size alpha or learning rate alpha is not 0, we can do essentially the same thing. So every time we compute this gradient on ith data point, we store it somewhere. And then in the future, if we want to compute this gk, we just set y to be exactly this stored gradient. And essentially, why that should work, that as xk converges to x star, also, or x star, which is the optimum, also then this gradient fi of xk converges to gradient fi of x star, but also yk will be converging to gradient fi of x star. So therefore, since those two things really converge to the same thing, that means like that this covariance of y and f goes to 1, and consequently, this variance of gk goes to 0. So again, if you didn't catch really how those things are constructed, it's not that important. The point is that this variance reduction is essentially some trick how to construct this yk on the fly such that variance of the gradient is relatively small. Okay, so given that we have this strange algorithm, how fast is that? So it turns out that one can show that this strange algorithm is essentially as fast as gradient descent in terms of number of iterations. I'm slightly lying here, but one can think of it that it's as slight as gradient descent under some assumptions. And how easy is to implement it? I mean, every iteration, we just need to compute one gradient of fi, so it's essentially n times cheaper than gradient to implement. And what is also nice about this thing, that one can show that such algorithm is in some sense optimal. So what I mean by optimal is that if we mix this strange gradient estimator with some form of momentum, one can show that you cannot do better than this. And how to show something like that? So it turns out that there is a result in the literature that if you have any algorithm, let's call this algorithm A, that for any algorithm A, there is some problem such that this algorithm A is doing poorly on that problem. And poorly means that it doesn't solve that problem in less time than some time t, let's say. However, what was also shown that this variance reduction district coupled with momentum solve any problem in time t or less. So therefore, I mean, there cannot be a better algorithm than this in general. Okay, and also really all those claims I said, it's up to some constant factor. So it's not really as fast as gradient descent, but there is some factor of 4. It's 4 times slower. It doesn't have n times cheaper iterations. It has like n over 2 times cheaper iterations. And so, but those things are just constant. So if really this n is large, this is really algorithm of choice. Let's talk about deep learning, because so far those results were some general results from optimization theory, which somehow apply to machine learning, but we will see that deep learning, which is essentially very specific application of machine learning, which is especially nowadays very popular, like in deep learning things behave differently. Okay, so what or how optimization in deep learning looks like. So probably some of you are some practitioners who are training some neural networks and so on, and I bet you never heard about those variance reduced algorithms, and I bet that many things I said so far, I mean, your current best practices, I mean, disagree, or you are not doing those things in practice. So let's talk about like really how to then train the neural network. So what people usually do in practice is that if they want to get some first result, they use Adam, which is some optimization algorithm I will talk about soon. But essentially, it's just a variance of stochastic gradients. However, also this Adam only works well when the network doesn't have too many layers with some kind of normalization. If the network has those layers, then this Adam doesn't work. Then what people do is then they get the best results using some tuned SGD. So this Adam is usually used just to get some first result, say that, okay, yeah, we can train things somehow, but if you want to get to train given model in the best way, usually people tune stochastic gradient descent in very funny way and use some very non-intuitive learning rates, which are not really predicted by any theory and so on, but for some reason those things work, and it's kind of, it requires some level of engineering to get those good results with SGD. Also, what is not nice in current deep learning practices is that if one uses some less standard architectures and more wild architectures of neural networks, usually one needs to tune the optimization algorithm quite a bit. And those non-standard architectures usually, or they can include some generative adversarial networks or some network with some Bayesian layers or something. By the way, those Bayesian layers are quite useful if you, instead of just prediction, you want to also learn how uncertain you are about your predictions. So once you want that, you would like to maybe have some Bayesian layers, and in that case, training gets a little more tricky. And what is also not nice that sometimes you have some architecture, things work well, and you tuned everything, and then you realize, okay, I want to add something, change some layers a little bit, and so on. Often, I mean, changing the architecture requires, again, tuning the optimizer again. When some learning rate at beginning was good, it doesn't mean it will be good after you change that. So the goal, I mean, of this area of research is essentially come up with some robust optimization, something which is more universal and requires little or no tuning. Okay. So as I mentioned, usually in those best practices, people don't use variance reduced methods. And the question is why? I mean, we said that those things are somehow optimal. So why is nobody really using them? Okay, so first thing is that usually currently, most of deep learning models are very overparameterized. So usually number of parameters is bigger than number of data points. So if you sum up size of all layers of your neural network, that can be even like 50 times more than number of data points. And remember, number of data points is already millions. So problems like that are usually very hard. And yeah, and often thanks to this high number of parameters, what we can say is that those gradients, fi and x star, which is optimum, they are zero. So that really means that we fit the data perfectly. Usually when you have more parameters than data points, that means you can fit the data perfectly, and this is somehow observed in current practice. And this is what really people are doing. Another reason why those variance reduced methods failed is that they are more somehow, they require objective to be somehow smooth, and neural networks are not really smooth. So as mentioned at the beginning, what we require to get those kind of convergence rate that I was mentioning, this 1 over k or 1 over square root of k, is that function f has Lipschitz gradients, or that gradients don't change too much. In fact, in neural network, this can really happen. And for some reason, those variance reduced algorithms are more sensitive towards something like that. And yet another thing, which is somehow strange, is that stochastic gradient descent is way better in practice than in theory. So as mentioned, this non-convex stochastic gradient descent rate is 1 over square root of k. So that means if you want to decrease your or get like 1,000 times closer to optimum, you need to do million of iteration. But usually, if you look at how 1 over square root of k as a function looks like, and how when you train the neural network, how is loss decreasing? Usually the loss is decreasing way faster than this. So the question is really why this happens. And all three things together caused those variance reduced methods to fail. So there was one paper in 2019, essentially last year, which made some experiments with these variance reduced methods. And what it essentially shows that here in this x-axis is epoch, or how far are we in the optimization. And this y-axis is the variance of stochastic gradient. And if the stochastic, or if this variance is in this red part, that means that this variance reduced gradient is not really helping, or it means that it's making things worse. And you can think of it that here on left, we have some small networks, and on those small networks, somehow this variance reduced gradient is helping, and we can see that the variance is decreasing. So those dots means that if it's some dot somewhere, it means that on 50th epoch, the variance reduced gradient had here like twice less variance than non-variance reduced, or the plain SGT. And if it's in the red, it means that it has bigger variance. So we see that on those plots on the left, that they really show that for smaller network like LeNet or some smaller SNet, those are networks with very little number of parameters. Their variance reduced method helped. But once you do some bigger networks like some DenseNet or ResNet and so on, those things has really huge number, like maybe 100 millions of parameters, or it's just something huge, the number of parameters. In that case, often what happens is that this variance reduced gradient is just making things worse. The variance, which was supposed to decrease, actually increased. So this really shows that why nobody is using those things. Okay, so as I mentioned, Adam is one method which is currently one of the most popular to train deep networks. So let's talk about that for a moment. So for those who don't know Adam, it's some method introduced in 2014, and until now it has on Google Scholar like over 40,000 citations. So for those who are not in academia, this is, huge number. It really means that essentially everybody in the field knows about this method, and everybody who ever trained some deep network used this thing. And it's something rather complicated, and I will not really go through that, what is really doing, but I will talk about some properties of that method and so on. So I will not really say what is it doing, but I will say that why it's good or why it's bad. So to surprise of whole community, this paper was done in 2014. On 2018, there was yet another paper which essentially said that the whole theory which was done in this, which the original authors did, is wrong. So in that paper, the author shows some kind of that here is this method Adam, which converges this fast, and they show that in this new paper, they show that all of that is essentially wrong, and Adam does not converge. Okay, what does that mean? It really meant that the Adam as a method can really diverge on some problems. So if you train some neural network and start with some loss, then after lots of iterations, the loss can go to really infinity, even if you set everything as you should. So that's what they show in this paper. However, what is somehow surprising, that they proposed a way how to fix this Adam, and they proposed a new theory, but this theory is still, let's say, 100 times worse than plain stochastic gradient descent. And also in practice, this fixed version is worse than original Adam, which is something really strange, and that shows that how this theory of Adam is really doomed and why it's not good. What is also somehow strange is that Adam on its own also does not make sense. It's not like that the method is intuitively doing something good. It's not really. So, for example, if Adam is method for stochastic optimization, what it really requires is every iteration to compute some stochastic gradients. On the other hand, if you give Adam full gradients, then the method is essentially a version of normalized gradient. So normalized gradient is every iteration you compute the gradient, which is direction of the steepest descent. Then you forget its magnitude and you just move in direction, but you forget the magnitude. It turns out that forgetting this magnitude is something wrong, and you really shouldn't do that. To see that, I mean, if we look at two problems, one is minimize f of x, and another is minimize h of y, which is 1/4 of f to y. So essentially, those two things are really the same. One is just a rescaled version of the other. And now you apply some kind of algorithm to produce x1, x2, and so on. So you keep iterating and get better and better models. And then you also apply the same algorithm to solve this other problem. So now, what is somehow reasonable to ask that algorithm is that if this x is equal to 2y, then also xk, it will be equal to 2y. Because the problems are just the same, so it makes sense that the algorithm does the same thing in both cases. It turns out that this normalized gradient, or Adam, is not doing that. It doesn't even hold such kind of simple invariance. On the other hand, stochastic gradient satisfies that. So stochastic gradient is in some sense good, however, Adam is not. So why is that people are using that? Another thing somehow to see is that, as I mentioned, Adam doesn't really work well with normalized layers. However, there was one recent result. Okay, so one of those normalized layers is batch normalization. And that's a paper from, I guess, also 2013-14, which is essentially proposing a way how to some kind of normalization in the layers. And what people are, or what the authors argue, that this kind of normalization is somehow reducing internal covariance shift, whatever is that. However, there was a paper from last year, I believe, which essentially showed that this whole internal covariance shift doesn't make sense, that batch normalization is, first of all, not improving internal covariance shift. Also, they showed that this internal covariance shift is not helping anything. What they showed is just batch normalization is somehow making optimization easier or making the training easier, and that's the only thing it's doing. And also, one things to somehow see is that training deep neural networks is not the same as general non-convex optimization. And those deep networks are somehow very special. So probably this is the reason why Adam is working well. And if you look at some kind of very simple neural network, essentially where the objective is product of x1 and x2, and you can think of it is that in neural networks, what really happens is that you have some data point, then you multiply it with some weights, then in the next layer you again multiply it in some ways and so on. And let's say if you have no activation in between of those two things, then what you have is just product of two weights somewhere in the middle. So if objective looks like something like that, then if we plug in this objective like x1, x2, which is 1 point, and another point is y1, y2, where y1 is 2x1 and y2 is 1/2 of x2, then it's clear that both of those, if you plug, whether you plug the left thing there or the right thing there, the result is the same. This f is the same. So what is now surprising is that if you apply stochastic gradient descent to train this left thing and the right thing, those have different behavior, which is bad. Now, if you apply Adam on the other hand, it's also different, but it's somehow less different. It's more similar. So this intuitively explains why it's better. Of course, one would want to have something which is always better. And in some sense, I had the chance to work on something like that over my internship in Google this summer. But yeah, essentially, this is one reason why we think Adam is good. Okay. And besides of these strange training practices and Adam, that Adam is working or not working, there is also yet another thing in deep learning, which is called implicit regularization. So what is this thing doing is that usually when you train some neural network, then, and now on x-axis is somehow how many iterations you did or passes through the data, and on y-axis is the error. So this black thing is the training error, and this blue and red is some kind of two different measures of testing error. So clearly, it's nice as training error goes down, testing error also goes down, and this is something what is expected. What is somehow strange is that as training error gets to 0, so that means you fit all your training data perfectly, but you still keep training. You still keep training despite having 0 training loss. People observed that also testing loss goes to 0, which is what people in machine learning really care about. So why is that happening? It was unclear, and it's in some sense shocking. If you look at your network is over-parameterized, you feed your data perfectly, and you still keep training, you would expect testing loss go up to the infinity, but it really doesn't. And the reason why this is happening is because of so-called implicit regularization. So what is this thing saying? This is also one work from 2018. What is this thing saying is that if we now again have green points and red points in the space, and we want to classify them somehow. So now clearly, there is many different ways how to cut them such that you will have 0 training loss. Whether you choose this line or this line, you will always have 0 training loss and everything is okay. However, what those people could show is that if you train this simple classifier with gradient descent, it turns out it doesn't find just any classifier. It finds one which is so-called max margins SVM. I don't want to really explain what is it, but it's essentially something which has the biggest distance from both sets. So it's somewhere really in the middle, and it's the one which looks the most reasonable. So from that perspective, this gradient descent, besides finding global optimum, it also finds something which is in some sense good, and despite gradient descent not being designed to be good or to perform that well. So to sum up this section, what I wanted to say is that optimization has, besides doing what we designed it to do, it's also doing some other nice things, which are still kind of not explained very well. But essentially, if you train things with gradient descent, for some reason, it's finding good or good optima or good models. Okay, so my slides came to the end. So I guess we have now time for some Q&A, and we have lots of time, so feel free to ask as many questions as possible. So the first question is like, how do we implement this algorithm? Probably whoever asked was about those variance reduced algorithms, whether we don't need to remember the gradient sizes for all previously visited points. Indeed, this is a very good question, and I will share my slides for a moment. So it's a very good question, and it turns out the naive implementation of this variance reduced algorithm really does require to remember everything. However, there are some smarter implementation of that essentially what we will do, we will not, the standard implementation is that indeed what we do, we need to remember gradients in all, maybe not in all previously visited points, but in n previously visited points, which is for every I, we just remember the last gradient we see. Okay. However, it turns out what we can do instead is rather remember one point somewhere that we visited in the past, in the close distance, and every iteration, and once per time, what we do, we compute full gradient in that point. So instead of this phi ik, what we will have have here just one point where we will remember its gradient, I mean full gradient, all of that. So we will remember this expectation, and we remember this point. And then in the future, when we need to compute gradient fi in that point, we will just recompute it. So that will mean that every iteration will be twice as expensive. However, you don't need to store everything. Okay, what do I think about fast AI Adam W modification? To be fair, I don't know about that thing. I can probably look at it very quickly, but let me firstly answer the other question. So I will answer that in some time. So when you have zero training error and keep training, doesn't mean that you make zero gradient training step. How does implicit regularization do anything? Okay, so to be fair, in that case, we don't have zero training error. What we have is zero training accuracy. So again, I wasn't, that's my fault. I wasn't very precise in that sentence. So what I meant to say is that here in this slide, this is testing accuracy and training accuracy. So it's not loss, it's testing accuracy and training accuracy. So it means that we were able to really separate those points perfectly. However, still training loss is not exactly zero. It's just accuracy. So therefore, you are still able to train, and that's why implicit regularization does something. So despite the fact that you really solved the optimization problem, and really you can think of it is that if this thing is if x is giving you the separator or the line, there are two things. One thing is direction of x, which is really giving you specific line, and the other thing is the magnitude of that. So if the magnitude of this line or the x is large, you will still have the same line, you will be just more confident about that thing. So it turns out there is lots of also solutions or lots of those separators which has zero training loss, not accuracy loss. But yeah, that was a good question. So this thing really shows accuracy, not loss. Okay, how many random peaks of I do we need to make in order to ensure that algorithm will converge for most of X? I'm not sure if I understand this question correctly, but in general, the result is such that for if you have some X, then you will converge to some stationary or okay. If you look at convex problems, which are somehow easier, and they have the one single optimum, what we can show is that the distance of your current X or current model to the optimal one is somehow decreasing every iteration. So how many random peaks of I do we need? It really depends on how far your current guess or your first guess was to the real optimum, which is something you don't really have control of. But besides that, I mean, if this distance is fixed, I mean, that can be, I mean, there is theory for that. It's either 1 over k or 1 over square root of k, or it's exponential. It really depends on the setting and on the algorithm. Yeah. But as already said, for deep learning, most of those results are not really useful in the following sense that things in deep learning looks or works differently than on these general classes of function that usually people analyze. Okay, do I understand correctly that this implicit bias is dependent on good loss definition? Indeed, this is perfect question, and yes, it depends on good loss definition. In this paper, okay, in this paper that I mentioned here, what people could show is that this implicit bias, if you have some kind of loss function with some kind of exponential tail, which really covers softmax cross entropy and some other popular losses, this thing will hold. Yes, it's true that it doesn't hold for any loss, but I mean, for some reasonable ones, it does. Also, I mean, in this example, what we could show is that something like that, yeah, that we have just, I mean, two classes, they are perfectly separable, and we just have linear separator. What is also nice is that those authors were able to show that if you, let's say, have some neural network with some linear layers or stuff like that, I mean, just linear layers, let's say, without activation, they could still, or without non-linear activation, they could still show that something like that is happening. What could they also show is that if you have some convolutional layers, then also something like that is happening. But in full generality, this result was not established. Yeah, usually to get something like that in full generality, it's rather very hard. And yeah, but at least those simple results give us some idea, like why some things behave in some way and that otherwise wouldn't be understood. Is there some widely supported implementation for deep learning frameworks like TensorFlow? So I'm not sure if I understand widely supported implementation of what. For example, this algorithm Adam is implemented in essentially any deep learning framework like TensorFlow, MXNet, Gluon, PyTorch, anything. On the other hand, those variance-reduced algorithms, I don't think they are. The reason is just that they don't work that well for deep learning. For smaller networks and so on, one can somehow maybe make them work, but usually it requires more expertise to make them work, and it's just not worth it the time. So I'd say if your problem is not convex or not something nice, don't use that. If it is about neural networks, then maybe. Okay. Are there any tricks how to choose good loss or how to distinguish between good and bad loss, especially when the loss is complicated? Okay, it really depends. What is your problem and what is your bottleneck? So there are some ideas like how to choose a good loss in terms of optimization. But also, I mean, optimization is not really the only problem in deep learning. What people care about is more sometimes generalization. And yeah, some laws may be better in terms of generalization, some may not, but to be honest, we have no idea about it. Usually, I mean, in terms of optimization, if you want to choose a good loss, what makes sense is to have some kind of something which is smooth and doesn't, I mean, you can differentiate through that easily. So that would be something like squared loss. It's not good, for example, to use loss, for example, in classification, something which is absolute value, because I mean this will not be trained really well. So something more or less smooth makes sense. Okay, especially when the loss is complicated, for example, multitask loss. Okay, I'm not sure if I know what exactly you mean by multitask loss, but I mean, I know that, for example, if, let's say, the output space is something really large, I know that, I mean, not many people care about something like that, but I know that especially in Google, the team where I interned cared in some sense about some really high output spaces where, I mean, you do classification, but what you want to classify is, I mean, the output space is just something really large. So in that case, the goal, the loss which they somehow designed was somehow random on its own, such that one doesn't really have to evaluate the output of the loss on every single point. So, but this is rather some kind of implementation trick, and something like that was called negative mining. So it really depends, but from optimization perspective, the main idea is good loss should be somehow smooth if you want to train it well. Okay. Next point. So the main point of the optimization algorithm don't work well unless they are designed specifically for neural networks. What do you, with this knowledge, know? So also this is a little, I'm not sure if I understand the question correctly, but the reason why many optimization algorithm works for neural network is not that somebody came up with some theoretical idea or the way how to analyze things. Usually the reason is because people just tried many things, and lots of people tried many things, and they came up with something, and then they try to figure out the arguments like why something like that works. So indeed, those things are designed specifically for neural networks, but it's practitioners who often design those algorithms. I mean, one good example is, I'm not sure if some of you know Lars algorithm. This algorithm was, I think it's maybe 1 or 2 year old thing, probably 2-year-old thing. And what people could say is that they could train ImageNet in some really short time with this algorithm, because they were able to use really large mini batch size. So there is yet another funny thing about neural network is that if you, every iteration, as you have GPU or more computers and so on, what you are able to say, you don't pick just one data point. You are able essentially for free to pick many of those data points. But for some reason, generalization gets worse if you pick lots of those data points. And people don't really know why is that. There are some reasons, but in general, people don't really know why is that. Why you need to pick a relatively small number of that. And this algorithm, Lars, was somehow able to go around this, and they were able to use really large mini batch size on lots of GPUs and lots of machines, and they were able to train ImageNet very fast. On the other hand, that method was rather some kind of heuristics. They had some intuitions, but I wouldn't say it was anything strong. On the other hand, what we were able to show during my internship in Google, and that work is still in progress, is essentially that this Lars, or some variant of this Lars, is, I will share the screen again, is essentially, it's essentially smarter than Adam, in the following sense that here, as we saw, that there was some problem on which, I mean, SGD didn't work well because the behavior was somehow different on two different initializations despite them doing the same thing. And Adam was less different. We were able to show that in some sense, Lars is part of some class of algorithms where something like on problems like that, the algorithm works well. And somehow neural networks have similar structure. So this is, I mean, one reason why this works. And based on that, we were able to improve upon Lars. So probably this is one way how to use this kind of theoretical knowledge to design something better. But I'm not sure if I understood the question correctly. Okay, and what do I think about this fast Adam modification? Is that they do some kind of weight decay or L2 regularization. So what is this weight decay really doing? Is that every iteration, besides of computing some stochastic gradient and moving in that direction, we will also make our weights somehow smaller. And that somehow, usually this string to make weight smaller. Okay, let me share the screen and share my slides again. So just for those who don't know what weight decay or L2 regularization is. So somewhere at the beginning, our objective was something like that. What do? We minimize average of n functions where this is f of x. So if we add at the end this objective something like norm of x squared, so L2 norm of x, and what we do minimize this plus norm of x, in some sense there are several reasons to think why this thing is good, but from optimization perspective, it's somehow making optimization easier. So what does it mean making optimization easier? Is that if you have here, if you, let's say, want to do gradient descent on objective which has this L2 norm there, and let's say that if your objective was originally convex, you add this thing, then it is strongly convex and the rate is better. Also, the more weight decay you add, the bigger this thing C is and the faster exponential rate is. So in some sense, the weight decay is doing something like that. And what is this Adam W doing? So what I understand is this Adam with weight decay is doing is somehow keep adding every iteration some different amount of this L2 laws, and maybe it gets smaller or something like that. But anyway, probably it will be better to, it's probably not good to answer it that quickly. Maybe, I mean, whoever asked that question, maybe we can just take it offline after this talk and discuss that later on. Probably let's just do that. That seems the most reasonable. I mean, it would take me maybe 5-10 minutes to really understand what this thing is doing. So yeah, sorry that I'm not able to answer it now, but please ping me either after the talk or in these group discussions after, and we'll somehow figure that out.